That's okay. Or you can just like that. Oh, no, I'm kidding. Oh, my gosh. Oh. It's good. Yeah, that's the. You just like. Oh, that's so good. I mean, just because he doesn't mean he won't. Yeah. I think that I probably would say that. We don't know the crowd. That's something. I'm grateful. My question's yeah. Oh, do you use different? Which ones? I use the zero alert. They don't get bio. Like, do you like? I know. It was Thursday. Like, wait, go to lab. That's fine. Yeah, exactly. Yeah, me too. I can see. I got 7 and I remember the line. Is it just so bad? That's okay, but like obviously you're gonna know. Like I know, no. I'm sorry. What? It's like what? She's not in the passport. I thought it was like it's I don't know. It's something like this. We get about that. See, like no. He's like, don't be careful. The couple is something. Oh my God, they didn't have it. Why?
What is green space is the part? What is green space is really hard.
Yeah. And it's serious.
Why are they doing it? So sorry. So the market's already.
Like I'm not.
Your homework page code 14.
Not today.
So you went out. Yeah, you picked the trade shares.
It was a tough weekend. That won't be the norm.
Okay.
I can't do it. Hey, bro. Dude. I don't know. Right. You feel like I'm done. I haven't got a chance. Bro, I was like, the audience. Vikings defense, that was big. I was like, that was like 20%. And it's DMC,
Utility.
I do.
Okay, if you can turn to page 10. Let me just go through Rolle's theorem with you. Rolle's theorem and mean value theorem are essentially the same thing. So with mean value theorem, the idea is that whatever slope I find between the endpoints, I can guarantee to find that slope somewhere on that curve. It could be a slope of 1/2, could be a slope of 2, could be a slope of 5. And then the conditions that's required is continuous with brackets and differentiable on parentheses. We have to first confirm that the graph is connected, that there are no hidden asymptotes or holes or sharp turns. If we can guarantee that, then whatever slope we find between the endpoints, there must be that steepness somewhere along that curve. But that slope could be anything. It could be 2, could be 1/2, could be 3, could be 5. Rolle's theorem is looking for specifically slope 0. And the reason that we have a special theorem for that is because most of the time we're trying to find a max and min. So we're looking for slope zeros more than any other situations. And so there's that special theorem to indicate that we're looking for that slope 0. But essentially it's the same formula. It's just that if we want Rolle's theorem to occur, we just want to show that the slope is 0 before the slope to the endpoint is 0 before we confirm finding that slope. So really, it's the same theorem. It's just that when we find the endpoints, we just want to ensure that it's a slope 0, and that's it. That's the only difference. Mean value theorem can be slope 0, can be slope 5, could be slope 50. But Rolle's theorem is specifically trying to trying to focus in on that slope 0. Okay, so let's just jump to example 2, and I just want to show you what that looks like here. Determine if Rolle's theorem can be applied for our function on the interval from 1 to 2. If so, find the value of c such that f prime of c is equal to 0. So it's the same formula. We just have to confirm that this piece needs to be 0 before we can move forward with the rest of the theorem. Okay, so we have a nice polynomial here. There's no holes, there's no asymptotes, there's no sharp turns. So we know that our conditions has been met. Okay. And just like with mean value theorem, you're just trying to gather your order pairs initially. So let's plug 1 into the function. So 1 for x, I get 1 minus 3, negative 2 plus 2 is 0. I plug 2 into the function. 4 minus 6 is negative 2. Negative 2 plus 2 is also 0. So once we have our endpoints, we're going to find our slope between the endpoints. So change in y over change in x. So I use that notation to indicate that I'm working on this side of the puzzle here. I'm trying to figure out that average slope, the average rate of change. So change in y over change in x. Okay, am I getting a slope 0? Yes. Okay. Now, do these have to be 0 in order for this to end up being 0? As long as these are what? The same, yeah. So it could be 3 and 3, could be 5 and 5, could be 7 and 7. As long as that slope between the endpoints is 0, we call that Rolle's theorem. But we could also call it mean value theorem. It's just that mean value theorem has a wider range of average slope that can exist. But for Rolle's theorem, it's specifically for slope 0. Okay, so now that we've confirmed that this is a slope 0, we're going to work on our derivative. And then we're just going to set the derivative equal to 0 and find the location on the curve where that guaranteed slope 0 is going to exist. Okay, so f prime. So now all that we're doing is we're just setting that derivative equal to slope 0. So it's basically finding a critical point. So this tells us that on this parabola, there's going to be a slope 0 when x is equal to 3/2. So for Rolle's theorem and mean value theorem, you're going to treat them the exact same way. It's the exact same formula. It's just that this piece has to be 0 if we want to call it Rolle's theorem. But if that's anything else, including 0, then the larger umbrella is mean value theorem. Okay, so that's all there is with Rolle's theorem. It doesn't it's not any different than mean value theorem. It's just a more specific version of it. Okay, so today we're going to move into more curve sketching, more specifically curve sketching content. So page 19. This is called the first derivative test. You're going to recognize this because this is a lot of the same thing that we did with particle motion. Okay, so what does the derivative represent? Derivative is simply another fancy word for slope. So it's the slope of the tangent line to our function or our curve. When the function is increasing, what's common about the derivatives is that you're going to get a derivative that is greater than 0. So any derivative that's greater than 0, that's just indicating that the slope is positive. If the slope is positive, you know that your graph is going to be rising on that interval. When the function is decreasing, then what's common is what we know about the derivative is that all your derivative is going to be negative if your function is decreasing. So when f prime is greater than 0, positive slope means my graph is rising. When f prime is less than 0, that means negative slope. That means my graph is decreasing. When f prime is equal to 0, that means my graph is a constant. It just means a horizontal or a changing direction. So any of these parts of graph would be slope 0. Could be part of a hill, could be just flattening out, but then still rising or decreasing, neither peak, neither max or min, or it could be a minimum. So when we go through what we call this is the first derivative test, this is a way of gathering where our graph is going to be rising and falling and where our slope is going to be 0. We're just going to go through essentially the same steps as particle motion. With particle motion, we said, we always set velocity equal to 0, right? Same thing here. We're just going to find f prime and set f prime equal to 0, find our critical points, populate our number line, and then indicate with positive and negative. But now, instead of positive and negative representing right and left movement, positive and negative just indicates whether the graph is rising or falling. So we're using the number line to kind of get a visual picture as to what the actual graph is looking like. So there's all these steps, but I think it's just easiest if we just went through the example and I can just walk you through the steps as we do the example. So let's try example 1. It says determine the intervals where the graph is rising and increasing, decreasing. Also locate relative extrema. So relative extrema just means relative max and mins. Okay, so just like with particle motion, you're just going to find the derivative and set that equal to 0. So we're going to find f prime. All we need is power rule. So 1/3 x cubed, bring down to 3, subtract 1 from the exponent. 3 and 1/3 will cancel out. I'm just left with x squared. 5/2 x squared, bring down the 2. 2 and 1/2 cancels out. I'm left with 10x, sorry, 5x because the 2's cancel out, plus 5x. Negative 6x becomes minus 6, and the 3 goes to a 0. Right? Once you have f prime, just like with particle motion, you're just going to set equal to 0. And it looks like we can factor this, right? Multiplies to be negative 6, adds it to be positive 5. Positive 6 and negative 1. Set equal to 0, solve for x. I get negative 6 and right, just like particle motion, you're just going to, instead of calling it a v of t sign line, you're going to call it f prime sign line. Place your critical points onto your sign line. Choose values in each subinterval. And we'll choose negative 7. I'll choose 0. I'll choose 2. But you can choose other numbers as well, as long as they fall within the interval. And then we plug into our derivative. I like factored form because we can just gather the signs without having to do a bunch of calculations. Negative 7 plus 6 is negative. Negative 7 minus 1 is also negative. 2 negatives makes positive. Now, when you put a positive, I think what helps if you can also indicate the slope that this is experiencing, because this will kind of give you a visual as to what the graph will look like. So I like to draw an arrow that indicates how the graph is moving. It's rising from left to right. Okay. Plug 0 into the derivative. 0 plus 6 is positive. 0 minus 1 is negative. So a negative. Before, we would consider that going left, but now we're talking about the shape of the graph. So a negative derivative means a negative slope. So just draw an arrow that indicates the negative slope. Plug 2 in, positive times positive. So this is indicating how the graph is moving. It's rising. So this is what the graph, the arrows is indicating what this actual graph is looking like. Without graphing it, we're using the derivative to kind of give us an idea. So the graph is probably going to look something like this. It's going to rise, hit a relative max, fall, hit a relative min, and then rise after that. Okay, so we're just going to indicate where our graph is increasing, decreasing. So for increasing, we'll say this. We'll say f of x is increasing on the interval from negative infinity to negative 6, and then from 1 to infinity because f prime is greater than 0. And we talked about how once we have our test points and we have our signs and our arrows figured out, we don't use those test points on anymore. Those test points are not going to show up in your interval statement. So this is important here. When we provide justification, you want to be able to say because, and the reasoning is because f prime is greater than 0, right? F prime greater than 0 is indicating positive slope, and that's why we know our graph is increasing. Okay, where is our function going to be decreasing? Yeah, negative 6 to 1, and the reasoning is similar because f prime is less than 0. Next up, we're going to locate relative extrema. So what can you expect at negative 6? That there's a what? Based off the arrows here. Relative max. Yeah, so you see the graph is rising, followed by falling. You know there's a relative max at x equals negative 6. We don't know what the y value is, but it's actually 51 here. How do you think we can find that y value? Back to the original. Yeah, so this is found by inserting that negative 6 into the original function, and then your calculator, in this case, would return you 51. So sometimes the problem would ask you for the full order pair. Other times it would just ask you for the x value. So it just depends on what the problem is asking you for. There's also a justification for relative max. And this is important because a lot of students do tend to leave this out. a lot of students are pretty good about increasing, decreasing, needing because statements, but then for relative max and relative min, for some reason, students just tend to leave the reasoning out. And the reasoning is because f prime, our slope is changing from specifically from positive to negative, and that specific order is causing the graph to experience that relative maximum. Same idea, relative minimum. This graph does experience a relative minimum because we have a negative slope followed by a positive slope, and that falling followed by rising is causing that critical point to be a relative minimum. And if I want to find the y value, I would insert that 1 back into the original function. In this case, it gave me a decimal. And then there's also a specific reasoning for that because f prime changes from negative to positive. Okay, so put a star next to these two. You'll be expected to provide reasoning for all your for your increase, decrease, relative max, relative min. But then this is where students tend to lose points because they would not include the because statements. Okay, any questions? Right, page 20. Okay, let's look at the function where it's not necessarily a polynomial, but we can still create a slope sine line to give us a picture as to how the graph is behaving. So to determine the interval where the graph is increase, decrease, locate relative extrema if it exists. Okay, so I'll say if it exists. Sometimes they may ask for it and they may not exist. If it doesn't, then we have to indicate why. Now, before we even look at increase, decrease, and relative max, relative min, let's just find some important information here. What do you know about the graph just by looking at the setup? Yeah, there's vertical asymptote. That's an important key feature there because that is going to help us have an idea that give us a bigger picture when we create our sine lines that maybe some critical points may not end up being a relative max, relative min, because we already know that there's a vertical asymptote at x equals 3. And so we know there's a break there. If there's a break there, there can't be a relative max, relative min, right? So that's an important visual feature for us to recognize. Okay, so now anything with increase, decrease is going to come from the derivative. So let's go ahead and find f prime. So to find f prime, what's needed here? Push a rule, yeah. So let's go through quotient rule. So f prime, 5x plus 2 times 5. All right, so remember, whenever you're cleaning up your derivative, that you're not ever canceling out between numerator and denominator, that you're just spending your time just with the numerator and leaving the denominator alone. Okay, so numerator gives me negative 17, denominator gives me x minus 3 squared. Okay, where do we look for critical points? Numerator and denominator, right? So we're going to look for them by setting the numerator and denominator equal to 0. Is the numerator going to give us anything here? Okay, so there's none here. But the denominator, we are going to get what? x equals 3. Now, even though there's a vertical asymptote at 3, we still want to consider that as a critical point that lands on the number line. We just know that that point is of asymptote, but it's still going to be important because even though there's an asymptote there, it will still separate your intervals of increase, decrease. So here's my f prime. The only critical point that I can get out of this is x equals 3. So place 3 onto your derivative sign line. Take points on either side. It doesn't matter which points you choose. Insert back into your derivative function. If I plug 0 in, anything that's squared is always positive. So negative over positive is negative. My graph is going to be decreasing. If I plug 4 in, numerator stays negative. Denominator is all still positive. Now, even if the arrows were going from down to up or from up to down, we know that despite what the arrows are telling us, this can never be a relative max or relative min, right? Because we already know that there's a break there. So now the only thing that we can say, okay, obviously there are no relative extrema. The only statements we can give is with decreasing. So the only statement that we can provide is that our function is decreasing from -infinity to 3 and the union from 3 to infinity because f prime is less than 0, no relative extrema for our function. Now for decreasing, can I say -infinity to infinity because they're both negatives? I can just combine it into one statement. Why not? Yeah, there's an asymptote, right? At that point, there is no behavior, there's no decreasing going on because that nothing there exists. So now there are times when you can merge different the same behaviors into one statement, but I think the safest thing is just always separate it. You're never going to get points taken off because you separated when you could have combined, but you may lose points if you combine when you're not supposed to combine. So I just find it easier to just always separate, and that way you don't have to worry about, wait, should I be combining it or separating it? Because you're never going to be losing points if you don't combine. So might as well just be on the safe side and just always separate. Okay, so always separate across, even if you could combine, if you have the same behavior, still separate them, always separate them into separate intervals. Okay, example 3, we're going to come back to when we talk about interpreting a derivative graph. So let's go to the next page here. Okay, so just want to get all the notes out of the way here from 5.3. Page 21. Before I called it concavity test, but I think the better name for this is test for concavity. The test for concavity is going to be different than the second derivative test. The second derivative test is for something else, so we'll talk about that in a second. But first, the test for concavity is the idea that if I have a graph that has this curve versus this curve, what do you know about their slopes? They're both what? Yeah, they're both positive slopes, right? But their curvature is different, right? This this slope, the slope as we move from left to right is continually increasing, right? It gets steeper and steeper. So maybe the slope of 2, then 3, then 4, then 5, then 6. Meanwhile, this is a positive slope, but what do you notice about the slope as we move from left to right? It's decreasing, right? It's still positive, but then maybe like a slope of 4, then 3, then 2, then 1. So, so both of these functions are increasing. That is true. However, the rate of their slope the rate of their slope change is different. So anything that resembles part of a graph that looks like a parabola opening up, we call that concave up. So you see this first graph kind of resembles more like a concave up graph. So concave up graph means your slope is always moving towards a positive direction. So let me just show you what I mean by that. I'm just doing ballpark values here, but this point could maybe be a slope of -4, right? Then -3, then -2, then -1. Then it's going to hit slope 0, and then maybe 1, 2, 3, and 4 as it gets steeper. But if you look at the pattern here, all these slope values are moving, becoming more positive, right? -4, -3, -2, -1. Imagine if you're on a number line, you're going to be constantly moving to the right, right? All these values are, and then if your slope value is moving towards a positive direction, the graph that's going to show up is going to be portions of a parabola that looks like it's opening up. Meanwhile, if I have a graph that resembles a parabola opening down, then the slope behavior from left to right is going to be one that is going to be decreasing. So maybe this could be a slope of 5, then slope 4, then 3, then 2, then 1, slope 0, -1, -2, -3. So we consider this graph to be concave down. Now, anytime we're dealing with concave up, concave down, we're dealing with the second derivative. So when we're getting to the second derivative function, if your second derivative is positive, that means your graph is going to have portions of this curvature showing up. If your second derivative is negative, then your graph is going to have portions of this concave down. Now, it doesn't mean that we're going to experience the full curvature, but we're just going to have maybe just portions of the curvature showing up. But if anything resembles portions of it, it's still considered concave up, right? This is not showing the full concave up shape, but this is still considered concave up. This is not showing the full concave down shape, but this is still considered concave down. And then finally, we have something called this point of inflection. Point of inflection is where your curvature is going to transition from one shape to the other. So let me just show. So we call this a point of inflection. I'm going to abbreviate as POI because you see that there's a concave up and then transitions to concave down. So that transition point between the two different types of curvature is called a point of inflection. But it can also go the other way. It could also go from concave down to concave up. That is also a point of inflection. So visually, it's just imagine two parabolas that are linked up, and imagining that transition point is where your point of inflection is. This may not always be true, but I think something that helps us to visualize point of inflection. So imagine the steepest parts of your graph. The steepest parts of a graph usually is going to be where your points of inflections are. So imagine if you're on the roller coaster ride, the parts of the graph where you're going to experience the steepest part is going to be the point of inflection here. So if you imagine the steepest parts of the graph, that usually, and that transition point is where that point of inflection is. Okay, so let me show you what that looks like in terms of our sign line. So imagine what we just did with sign lines for f prime. We're going to do the same thing, but then at the f double prime level, we're still going to test critical points. We're still going to test positive and negative, but now the positive and negative is going to mean something a little different rather than increase, decrease. Positive and negatives will just represent concave up, concave down, and then a change in sign would indicate point of inflection. So you're going to repeat the very much the same procedure with first derivative tests, it's just that now you're doing it at the second derivative level. So 5 points of inflection and intervals of concavity. So we're going to have to make our way down to f double prime before we look for critical points. But we have to first get to f prime first. So f prime, we go through power rule. Five thirds x cubed becomes 5x squared. Okay. We're going to keep going. We're not going to set f prime equal to 0 because we're not asked about relative max, relative min. So we're going to keep going down to the second derivative, set f double prime equal to 0. Sorry, f prime, double prime first. Go through power rule. Now set f double prime equal to 0. Find your critical points at this level. So take out your GCF and x. So if you're taking out GCF, that means you're dividing your initial terms by your GCF. Oh, sorry. Yeah, I think it's 4 is plus 4. Okay, so now I can set both equal to 0. The left side is easy, x equals 0, divide by 10 here. I'll divide both sides by -4. I get x squared is equal to 1/4. Take the square root, x equals plus or minus square root of 1/4, which is plus or minus 1/2. All right, so very much the same way, you're going to now call this a second derivative sine line. Place your critical points onto your sine line. In this case, we have 3. So -1/2, 0, and 1/2. Pick points in each subinterval. So here I'll choose -1. Here I'll choose -1/4. I'll choose 1/4, and then I'll choose 1. I'm forced into a decimal here just because, or fractional, because I'm between 0 and 1/2, so I don't have a whole number that I can fit. So I just used 1/4. Now you're gonna make sure that you're plugging this into f double prime, right? We're talking about f double prime here, so make sure you put it into the f double prime function. And then we're just gathering positive and negative signs here. So negative into x, this is negative. -4 times 1 squared is still negative, plus 1 is negative, so 2 negatives makes positive. Now, at the second derivative level, a positive doesn't mean increase, doesn't mean slope is positive or negative. It means concave up. So to help you see visually what's going on here, I like to do a parabola opening up to indicate that this part of the graph is going to resemble this shape. It may not be the full concave up shape, but it's going to resemble that curvature up shape in this interval. Okay. -1/4, plug -1/4 in for x. I'm still getting negative here. Here it'll give me a positive. So negative times positive is negative. So on this second interval, my graph is going to be experiencing concave down shape. Okay, plug 1/4 in, positive times negative is, sorry, 1/4 in for x. I'll get 1/16. -4 times 1/16 is going to be a -1/4. Plus 1 is going to be positive. So positive times positive is positive. And then plug 1 in, positive times negative is negative. So stating all the intervals of concave up and concave down, you're just reading it off the sine line. So we can say f of x is concave up. Oh, and most, yeah, so anytime we do increase, decrease, relative max, relative min, or concave up, concave down, all your intervals will be parentheses. You're never going to see brackets. It's always parentheses. So concave up in the first two intervals here. And again, we don't care about the test points, right? These points are not going to play a role. It's the original points from our sine line. Okay, we have because statements that we need to include. So we're going to say because f double, we're at the second derivative level now. So f double prime is greater than 0. Okay, that's indicating concave up. Concave down, these two intervals, -1/2 to 0. And then from 1/2 to infinity. The reasoning is because what? F double prime less than 0. Yeah. And finally, you see how there is a change in signs? It doesn't matter the order of sign change. As long as there's a sign change, we call them points of inflection. So we can say POI. I'm just going to list out the x values here. So -1/2, 0, 1/2. But if I were to ask you for order pairs, where would you find them from? Good, original, yeah. So anytime you're looking for physical points on the graph, they go back to the original function. And the reasoning is here because f double prime changes signs. If you want to specify the order of sign change, you can, but you don't have to. But for relative max and relative min from first derivative test, you definitely need to indicate the order of sign change. But here, point of inflection, we don't have a specific name for point of inflection, whether it's from positive negative or from negative to positive. These were all considered point of inflection. So it's less restrictions, less statements you have to make with your because statement. All right, last thing here, page 22. Okay, we have something called the second derivative test. And second derivative test is not the same thing as test for concavity. Okay. So this is a little strange here because the second derivative test is going to do the same thing as the first derivative test. It's using the second derivative function to gather information about relative max and relative min. So, you know, I think for us, if we're ever trying to find relative max, relative min, I think we're always going to prefer to use first derivative test. The second derivative test is kind of like a roundabout way of finding relative max, relative min. So let me just show, I think it's best to kind of show you a diagram here. So let's say I had a graph that looked like this. Okay. What is the slope at x equals 1? So let's just look at the graph here. So here, f prime of 1, what would you expect from f prime of 1? 0, okay? Now f double prime of 1, meaning the concavity, 1 is a relative minimum, but is this part of a concave up or concave down graph? So therefore, f double prime of 1 is going to be what? It's going to be positive, right? It could be 3, it could be 6, it could be 18. As long as it's positive, that's enough for us to know that, okay, so whenever you have this behavior in front of you, if your slope is 0 and your graph is concave up, you know that these two combined into the same location means that we must be staring at a relative minimum because your slope is 0 and it's part of a concave up graph. So we can conclude that there must be a relative minimum at x equals 1. So if I compare these two behaviors onto the same graph, I can conclude that there's a relative minimum without looking at a sign line or without looking at anything else. If my slope is 0, my graph is concave up, I must be staring at a relative minimum. Okay. Meanwhile, imagine a graph that looked like this. But now let me call this point 2 here. Here, f prime of 2 would be what? 0. But here, f double prime of 2 would be less than 0. So this number doesn't matter. Okay, it's going to feel a little abstract, but if you see -61 or -4 or -3, it just means that it's different it's just different curvatures of that all represents concave down. So as soon as you see slope 0 and concave down, you know that you must be staring at a relative max at x equals 2. Okay, so we're going to try to narrow down one of these options as we work through our problem and see if we can show whether it fits slope is 0 concave up or slope 0 concave down, and use just these two rules to help us determine whether we're looking at a relative max, relative min. Okay. So first thing is we're going to find f prime. We're going to find our places where slope is 0. So rather than using the sign line, we're going to force ourselves to use the second derivative test. Okay, so set f prime equal to 0. We're going to factor. Multiplies to be -9, adds it to be -8. Solve for x. Okay. This starts off initially looking like first derivative test, but rather than putting onto a sign line, we're going to insert them into second derivative function. So let's find f double prime. Power rule again, 6x minus 8. So now I'm going to insert them into f double prime. -1/3 and for 6, sorry, and for x, I get, which is -2 minus 8, which is -10. Now that -10 doesn't really matter. It's the fact that it's what? That it's negative. So if my graph, so if the graph is concave down, right? That's all that means. That -10 just means that you must be staring at the concave down, and that place has a slope 0. What can we conclude? There must be a what at -1/3? Yeah, relative max. So we're using this rather than our slope sign line. All right, f double prime of 3. (18 minus 8 is 10. 10 is not important. It's the fact that it's what? Greater than 0, and that means it's concave up, and concave up means relative minimum. Okay, I went through this a little bit fast, but we're definitely going to revisit this tomorrow. Okay, let me see, homework. Okay, your homework, page 25 to 26. I'll send out a reminder.
Can I check these?
Yeah, thanks.
Here.
Okay, great. Thank you.
You got on their bed, they're inside.
What?
Where's the menu? And then that's the third time. So then you have ungotten this jam here at the bottom of the box.
You just against what? Huh?
Your favorite ride, right?
Like Russell Wilson.
I don't know.